Welcome to the course on FPGA based signal processing systems. Today we will be looking at the CORDIC algorithm and the special functions which can be obtained through CORDIC. So the CORDIC stands for this coordinate rotation digital computer, where this is used for trigonometric functions and some of this like the cos theta, tan theta and sin theta computations through FPGA. So FPGA doesn't have a special functions to, I mean, in the code we will not be able to do it, though some of the IPs now getting generated for that. So here this is square root, finding a square root in an FPGA for terms like x square, y square root, and the trigonometric functions and other like dividing the two variables, also the logarithmic functions. It's can be done through this coordinate rotation digital computer. So how this algorithm works, what is the, how can we develop the Verilog code for this? Because this is going to be an iterative algorithm in which we need to make this module, Verilog module, for the iterative algorithm. Especially it involves 3 equations, so it depends on the coordinate system. The equations and the parameters would vary, so that can be modeled in the Verilog. So once we have this module, it will be able to test that in the FPGA for computing cos theta, sin theta and tan theta, as well as some of the other functions. So the Cartesian coordinate plane rotation. So if we take this point here over here, considering this is x1 and y1 point, in which this is x1 comma y1, the vector pointing this point, and then the point which is in the Cartesian coordinate, which is rotated to an angle theta, where it ends up with at a point y2. Okay, so this vector, this particular rotation, you can see this this is a circular rotation. Okay, circular coordinate in the Cartesian coordinate. The profile, you can see it is a circular. So at this particular point x1 y1 and the movement of x1 y1 to x2 y2, so involving theta can be expressed with this equation, that is x2 equal to x1 cos theta minus y1 sin theta. Similarly, y2 equal to this, y2 is x1 sin theta plus a y1 cos theta. So if we consider first, this is going to be the initial theta, and then if I by x1 y1, and this can be cos theta equal to x2 by x1, and this detail can be easily obtained in this relation from the diagram. So the two equations, how we are manipulating these two equations to get the theta or the sine of that, cos of that, is the challenge here. So this the two equations which can be again, so if you see write it in the matrix form, these two equations x2 and y2 equal to cos theta minus sin theta and sin theta and cos theta. So it's a 2 by 2 matrix with the two equations what we had, and x1 and y1 are the inputs. So this input, and if you get this point x2 y2 at the output, suppose this theta can rotate with the in the plane. So here the theta can be of different values. So if theta is 90 degree, for a simplified case in which that if you substitute here theta is 90, then cos theta is becomes 0, this becomes minus 1, and sin theta is 1 and cos theta equal to 0. So here x1 and y1, that is going to be minus 1 and minus y1 and x1. So resulting the product leads to minus y1 and x1. So x2 y2, now it's changing to minus y1 and x1 for the theta of 90 degree, this rotation vector wherever it is in initial. So if we have this to be 90, and then so 90 degree theta, so it results in a rotation. So this theta can be varied, that's what we are trying to say, this vector rotation in the matrix form. So if we have this rotation, it is also here is a circular rotation, the in which the vector rotates is the circular rotation. Whereas if considering these pseudo rotations, if we have this for theta 90 degree, this seems to be simple, but if you suppose the concept of pseudo rotation, if you consider here, so whereas see here x2 equal to x1 cos theta minus y1 sin theta, in which if you take the term cos theta common from this equation, so leads to x1 minus y1 tan theta, whereas y2 equation similarly, if we take this the cos over here, that becomes y1 this term, and then x1 is sin theta by cos theta, again this is going to be tan theta. So the cos theta term, so to reduce the effect of computing this cos theta sin theta every time, so we try to minimize this operations and in the process. So the cos theta term is can be dropped if theta is known, if you want to compute a cos theta for it. Okay, so that then it is then with the pseudo rotation we can see x2 equal to x1 minus y1 tan theta, the first equation here. So similarly this y2 can be dropped. So if you look at the y2 equal to y1 plus x1 tan theta by dropping these two terms, that cos theta, in the equation. So first we had this x1 y1 in terms of x2 y2 with respect to the theta, and then we try to minimize this using the pseudo rotation, the process in which has the addition and shifting that is possible in the FPGAs so very easily. So we try to using the pseudo rotations, we are minimizing this operations. So here the cos theta, once it is dropped, the x2 y2 now becomes x1 minus y1 tan theta and y1 plus x1 tan theta. Here is the rotation, we can observe that this is the initial position of that x1 y1 here. So if we have the true rotation, yes, this should move to the point here x2 y2 which we have seen in the previous diagrams with the theta. So we have the pseudo rotations, it's not going no more following this circular rotation here, it is the pseudo rotation in which that you have the exactly this is 90 degree from here. Okay, so if you draw a line over here and the magnitude of this vector is also increasing. Okay, so that is written as here r cap. So this point is now it's not x2 y2 and it is x2 cap and y2 cap. So this can be written over this, r is known, x1 y plus y1 square root, if you will have the magnitude, and if that r cap will be that r by cos theta term, that is the theta is involved in this, so the cos theta which is over here. So this changes the length of this vector r cap, which is governed by this by cos theta, x1 square plus y1 square root, and this is cos theta. So the pseudo rotation just to indicate the diagram that how it would look like in compared with the true rotations. So the after pseudo rotation we get this r cap, or the x2 cap and y2 cap. So the magnitude, as we said, the magnitude r is increases by a factor 1 by cos theta. So yes, obviously this magnitude is more than this. So it is the factor affecting this is 1 by cos theta over here. So now coming to the this would make rotations in terms of angle, that is theta. Okay, so the theta angle needs to be controlled. So how do we control this theta in the rotation? So x2 equal to x1 minus y1 tan theta, that is what we had after dropping cos theta. What is the expression we had, that is equal to x1 minus y1. So if you make this tan theta as 2 power minus I, so which is the expression simplifies this again to have the theta tan theta equal to x1 2 power minus I here. So we can see x2 and y2 in which y1 plus x1 2 power minus I. So tan theta power I equal to 2 power minus I. So if you assume that tan theta equal to 2 power minus I, then with this the equation changed here, so to that tan theta is 2 power minus I. Here also tan theta is changed to 2 power minus I, in which for now let's see how this variation is taking place, why this assumption will be applicable here. So the case here, let's look at this I, which is given over here. This is suppose the iteration. Okay, so I is 0 1 2 3 4 and theta power I is that the theta what we are the rotations we are aiming here, the vector how it can rotate theta. So for that tan theta power I equal to 2 power minus I, if you see that if for ith rotation, that is 0th rotation, I equal to 0, the very first one, then this becomes 2 power 0, this term is 1. Okay, so this is 1. When tan theta equal to 1, the theta is 45 degrees. So 45 degrees to start with. So after that, if this is the angle that 2 is now made it 1 here, 1 by 2, this is going to be 0.5, the angle is getting reduced half here, that is 26.6, and then this with the term 0.25, 0.125, 0.0625. So in the 0, 1 and then 2, it is 1 by 4 here, and 2 power 3 it is 8, 1 by 8, and then here again 2 power 4, 0.0625 here. So this can be easily used with the shifting. Okay, so the angle also getting half in this process. So this is round up to 1 decimal. So you can have this also with multiple decimals. So you can see the theta variation and the 2 power minus I. So for I equal to 0, so we substitute it here, getting 45, and then next is 26.56. So tan inverse of 0.5 this. So we can get this table. So that using the shift, and instead of this tan theta, this obtaining x2 and y2, just having this 2 power minus I. So x1 and y1 with y1 multiplied by, suppose this is going to be 1 or 0.5 or 0.25 and 0.125 and so on as iteration progresses. So now we have get rid of this theta computation, tan theta computation, and only it is shifting operation here. So now x2 y2, which we get through this using the pseudo operation and then applying the restricting angle theta to 2 power tan theta equal to 2 power minus I. So from this, then it is becoming, here you can see yi 2 power minus I in this first case. So we have, so xi plus 1. So to generalize that equation, xi, the xi is, suppose here is 2, I is 1, in that case it is x2 and x of I, the previous value. So the first one and then go to the next one. So to make it generalized, y power I 2 power minus I, in which this di is saying that theta, how do I rotate from one, whether it is positive rotation or it should go to the negative rotation. So we have as the vector should go in anti-clockwise direction or the clockwise direction. Okay, so then the yi, similarly yi plus 1 equal to yi power I plus di 2 power minus I xi. So these two equations now we obtain with this d is plus or minus 1, if this is going to be rotating in which direction. So where di is the decision operator used to decide the direction of rotation. So if we can see the particular equation, the third equation which is introduced in this case is az power I plus 1 equal to az power I minus di theta power I. So where the previous theta, okay, so this gives the theta I and then the direction also. Here is the value zi, which is having it is giving the angle accumulated so far. What are the, how many rotations have been taken during this time in the iterations. So it's actually called the angle accumulator, the third equation. So these three equations for Cartesian coordinate we have given, and then this can be generalized also for other coordinates, so that other functions are possible to get it from the chodic. So this x2, this is the equation from which we have generalized, just to give the one. So the algorithm now, it is now reduced to what is that first equation now becomes xi plus 1 equal to xi minus di 2 power minus I into y of I, and similarly yi plus 1 is y of I plus di 2 power minus I into xi. So this angle equation, which is z bar I plus 1 equal to zi minus di theta I. So what is that? This three equations required if you want to if you program it, then it has this two shifts, that is two shifts here. This is 1 2 power minus I and 2 power minus I. So depends on that, if 1 and then 0.5, 0.2, 0.125 and then 0.2. So this 0.25 and half of it can be 1 by 2, 1 by 4, 1 by 8 and so on, 0.125 next. So it moves that direction. So it is clearly indicating this two shifts are involved in the this computation. Also we need to, if you store the theta values, what are the theta values, it can have the one lookup table which has the theta values, also the three additions 1 2 3 which needs to be done. So how this is simplified. So now the next rotation x and y, x y and the z, the angle of rotation, how much angle it is rotated, so can be obtained through this. So this how can we use it for the computation. Also, before going to the computation, one is that scaling factor, which we neglected, the cos theta term in the process of developing this equation. So our outputs yn and xn are scaled by a factor kn. So that is yxi plus 1 or yi plus 1, whatever is computed, that is at the nth iteration. N specifies here nth iteration. I is varying from 0 to how many iterations you go for. So kn is that product of 1 by cos theta I. So how many 1 by cos theta we have neglected in each iteration. So that the product of this 1 by cos theta is giving it here kn. So if the number of iterations are known, then kn can be stored because those values lead to maximum 0.99991. So it can be pre-computed and put it in the table or in the for usage. So the next one, how to incorporate that the neglected cos theta can be added into the algorithm as a pre-computed value using the kn. So this can be, we have to also know that Codic method has two modes. One is the rotation mode and vectoring mode. How we can use that in two different modes to what can be computed from that. So suppose taking this the direction of d here, so d is the rotation mode, chooses this sign of z power I, which is where zi is converging to 0, this in the rotation mode, okay, where the equation z we computed. Actually first when we start with the angle x1 y1 and then it moves to x2 y2, the theta, initial theta, and then the theta gets adjusted plus or minus. So if it is plus, it moves in this direction, negative another direction, it keeps moving, and then that theta, what we want to compute for theta, suppose cos theta of 30 degrees. So if you start with 45 degrees and then move in one direction and other directions and so on, clockwise and anti-clockwise, depends on the di, sign of di, and then finally that angle, total accumulated angle, should come to 0. So it should arrive at the 30 degree computation. So after n iterations, what happens, this xn is that x0 cos z0, y0, this z of 0 is the theta which is calculated using that, and y of n is kn. Similarly, the other equation also has the cos. You can notice that z of 0 and this. So how are we going to do that in the So first assume that z of 0 initially, there is no angle changes in that 0, and then we can compute cos theta I, that is z of 0, cos z, that angle accumulator, and then sin z I, by starting with x of 0, which is in this equation, that the three equations which we had given, 1 by kn, and then y of 0 equal to 0. So if we assume that here di, so let us look at this, how we are going to do this, and di is nothing but sine of zi, so either it is going to be plus or minus, and then theta I is tan inverse of 2 power minus I. So it should be pushed here. So the three equations we had given, which we are going to use it for the computation. And iteration 1, what happens here, this I equal to 0, and x1, this is the first one, and this is 0. So this x of 0 is assumed to be 0.6073. Okay, so 0.6073 comes from kn, where number of iterations or n equal of cos theta, all of them has been multiplied and got this value 0.6073. You can see in the any FPGA IP model that if you have the Codic block, that Codic block will have this values used 0.6073, and this is x of 0, and now initially this di is positive, and then here is y of I, which is 0, and this is 1, 2 power I minus I, it is equal to 1. So which leads to 0.6073. The first value of x gives this 0.6073, and then second y1. So similarly, if we compute that y of the initial value is 0, taken as 0, so x of 0 value, which is 0.6073, note it down to compute a cos 30 degree. Okay, so here is that we have given in the previous case. So we can compute this cos and sine both by assuming these values. So coming to the first iteration of y, so this is y of 0 here, and this is plus and di is plus initially. That's there is no rotation. Assume this is plus, and then this is going to be 1, and xi what we obtained is here 0.6073. Okay, so this is x of 0, so this is 0.6073, what the value. So it's not x of 1, it is x of 0. So 0.6073, which also result in 0.6073. x1 and y1 are obtained, and z1, the first angle, so we are going to compute for 30 degree, that is the z of 0. Okay, so 30 degree and minus the equation d is plus, and 45 degree is the initial assumption. Okay, so assumption of tan I equal to 0, so this theta I is here 0, tan inverse of this is going to be 45 degree. If we compute it from here, this substituting is 45, that is minus 15. So we get this minus 15 now from 30 degree. Now minus 15 is rotated, so it would be rotated here. So minus 15. So if you take the z is minus 15, okay, the what we had obtained, the next direction di is minus 1, so di will be minus 1. So similarly, so x2, if we calculate it, that is from x1 the iteration minus 1 and the value and the 2 power minus 1, that is 0.5, it leads to 0.9109. So similarly y2 can be obtained, which is from the second iteration, and z2 which is leading to 11.6. so this is giving positive value, so the d2 will be plus 1. Okay, so plus 1. So from this we can obtain this table I, and then di here theta is at y and xi. So from this is 0th iteration, this was assumed 1, and the angle theta I is 45 here exactly, and then we are going to find out for the 30 degree angle, that is plus 30, and y is 0 and x is 0.6073, we assume these are the initial values, and then we computed for first one. So the dA we got it minus 1, and the angle from that is the half of it, that is 26.6, and from the z equation we got minus 15, and then this. So this minus 15, so which is used here, and then the here plus 1, that is 14, 11.6, and then 0.306, and so on. So we had 7.1, as we have seen this d progressing, also xi and yi. So this xi and yi, what we had here is that up to yi and xi we computed 9 iterations. So cos 30 degree here, and then the sign 0.866 instead of this 0.500 you are getting. So this is the error, instead of 0.5 we get 0.5006, and 0.666 it is small, the 66 getting the small error. So if we improve the iterations more, and again this error can be reduced further. So x and y now from the initial value, this is 0 and 0.603, we get the sin theta and the cos theta values. So in the rotation mode, so if you want to in rotation mode, so it keeps, one point is that it keeps reducing the theta. So we started with 30 degree, and then minus 15, and then plus 11.6, minus 2.4, and then plus 4.7, minus 1.1, minus 0.7, plus 0.2, minus 0.2, and 0. So it is converging to 0. So that means at the convergence we have this, still it won't move further. Okay, so in this case the z is from the angle what you are starting. Suppose this is the angle 30 degree, and then it would move to here, it would move to next angle if it is positive, or otherwise it will move to here. So from here to here, and then here, and then if there is anything like positive, again it would move within the angle, or if it is more than that, because this theta is not moving more than 30 here, you can see within this only it will be keep on moving from one to another, this way and this way, and coming to the 30 angle. Okay, so that 30 once it is achieving to 30, actually we want 30, but we started with the 45 degrees. Okay, so 45 degrees, so the movement will come to the 0, so that we get this value, what is the sin theta and the cos theta from that. So this is from the rotation mode. If we go to the vectoring mode, and that's d phi sin, we have x and y, where yi is leading to 0. So after this nth iterations, we have n iterations, we have x of n is kn x 0 square plus y 0 square root. So yn is assumed 0. So kn is known and x0 y0 are known in the vectoring mode, that is the rotation mode theta, so which is used to sin theta and cos theta there, and from that tan theta would also be calculated. So here is the x and y values, and y is 0, z is the equation which has the theta I, from theta I tan inverse of y by x. If you replace that theta I equation, 2 power minus tan theta per I equal to 2 power minus I. So from this we get tan inverse of y by x. So we can compute this tan inverse of y of 0 by setting this as 1, okay, and z of 0 equal to 0, initially 0, and this will be tan inverse of y of 0. So we can get by setting this as 1. So here what is using the vectoring mode, we can have this z computed 63.4, I is varying from that, and theta initially 45, and then it is yi from the equations we get from the previous equations also yi, and theta I and z is 0. So if you can see the theta I which is reducing in the fashion of half of that, and the 2 1 1 this y of I from the equations, and zi is the angle which 63.7, the angular accumulator from 0 it is keep on accumulating. You can see the angle accumulation in this process. So we can compute this tan inverse of y of 0 also. So rotation mode and vectoring mode can be used in the Codic process. So if we to consolidate that, this coordinate system, if it is a circular coordinate system, then x and y, x, y, z are the 3 inputs of the Codic if you consider this as a block, and zi is going to be 0 in the rotation mode. Di is the sign of z of I. So zi is which is initially assumed plus 1, that zi is going to be the plus sign, plus or the minus, which depends on the sign of this, and k is the kn here, the k value which is k x cos z minus y cos c. This is the first output, and second output k y cos z and x sin z. So if you cos z and sin z we want to obtain, then x equal to, set this x equal to 1 by k as we did, and y equal to 0. So if you do that, you can get cos and sin from this here in the rotation mode. In vectoring mode, similarly, yi is tending to 0. We have seen that equations, di is minus sign of x and y. So taking this x and y and its sign and moving over these equations in the vector mode x, y, z, the k what you get is square root x square y square root with k. Okay, so and you can also get z plus tan inverse of y by x. So the equations what we had said over there, this x and then corresponding, so tan inverse of y, and for that x equal to 1 and z is 0, so you will get tan inverse of y also. So square root and this tan inverse can be obtained from the vectoring mode. If it is a circular coordinate, these are the settings, initial values, and what are the what functions can be obtained from this Codic equations. So more functions can be computed if other coordinate systems are also used. So the other coordinate systems, like instead of having the circular coordinate, so if we have the linear coordinate, so they can see the line, the vector which is rotated from here to here or here to here, the angle which can have the angle that means the vector length which follows in the line. Okay, so this is a linear coordinate system in or it can be a hyperbolic coordinate system in which the initial vector may be this or this, and if it is moving, it is moving in the hyperbolic curve. So these two, instead of circular, we can have the hyperbolic or linear rotations. So the generalized quadic system, which includes this linear and hyperbolic coordinates. So this are the three. So we can see, so three equations. You can see the another one which is mu. Okay, so here we have this mu 1. Okay, in this equation, e power I tan inverse of -1 2 power minus I, whereas linear rotation this mu will be 0 and e power I is 2 power minus I. This is going to be tan inverse of -1 2 power minus I for the circular rotations. And then for hyperbolic rotations again mu is -1. Okay, so e power I, where e power I is changing to tan inverse h -1 2 power minus I. So difference of mu is set to 1 for circular rotation, and the e power I is tan inverse 2i tan h inverse 2 power I. So that is the difference in this. So easily that circular rotations and hyperbolic rotations can be done with the same setting of ei1 change. Mu is completely 0 and then this part would be 0. Here only xii plus 1, e power I is 2 power minus I. So that can give the linear rotations here. So let's see what are the things can be obtained through this. Linear rotations can give x, y, z and y, x and z product also, where z is moving towards 0 in the rotation mode. For multiplication, set this y 0 so that you get x is z here, and the vectoring mode yi is equal to moving to 0, as we have seen that z0 or y moving to 0, di the sign of this, x, y, z and x, and this is going to be 0. Here you can see the y by x, so z is set to z to 0 here. So multiplication and division can be obtained through this quadic when we operate in the linear coordinate system with this initial settings. So this can also be done in hyperbolic, where mu is given as -1 and then zi d and the same over here. So you get cos h's, cos hz, cos hz, sin, this is sin hz. So instead of cos z and sin z, or cos theta and sin theta, we get cos the hyperbolic functions, and this k star needs to be specified, and y0. Here is that again we in the vectoring mode we can obtain this tan inverse h setting, also x set 1, and here we have the square root as well. So vectoring mode helps in getting the square root of x square minus y square as well. So different functions can be obtained through this quadic, cos sine in the rotation mode, or cos h and sin h in the rotation mode of hyperbolic. Also vectoring mode can give the square root or multiplication. In the linear case it can give the linear coordinate system, it can give multiplication and division as well. So these are the general functions which can be obtained from the quadic. Apart from that, we can also get this once we have the sin z, cos z, tan z can be computed, tan h z can be computed. We have this in the hyperbolic, that is, this is in the rotation mode of the circular coordinate, and this is the hyperbolic, and tan inverse w minus 1 w plus 1 can also be obtained. Ln function can be obtained once you have this, and e power z can be obtained if you have these functions sin and cos. Also tan inverse of w can also be obtained from here, and sin inverse of w. Similarly cos h inverse, sin h inverse, and root of square root of w can also be obtained. So other functions can also be obtained from this quadic equations. So three generalized equations of the three equations of the quadic algorithm can be moduled. You write a Verilog code in which the three equations can be stated for different iterations, and the module can follow the iterations, depends on this set it to rotation mode or vectoring mode, and that should be one module which can at least work for rotation mode and vectoring mode of both the circular coordinates separately, so that we can get this theta, cos and sin theta, or the x and y values what is required for the in the circular coordinate rotation and vector mode. Similarly, for the linear coordinate, multiplication and division can be performed by setting the parameters. Also the hyperbolic coordinate, in which if we set hyperbolic functions can be obtained. Using these other functions can be. So develop the Verilog module of the quadic and practice this computing these functions here. I will also be showing the yes, smaller code which can perform for this CORDIC in the tutorial sessions. So thank you so much.